Thank you, TJ. So I have the great pleasure of introducing Anne Louis from Lund. I would be exaggerating if I said we all wouldn't be here today discussing this if it wasn't for Anne Louis. So I'm really happy that Anne has agreed to take the time out of her business schedule to be here. Just a little bit about Anne. Anne did our thesis work at this Saclay CEA in Paris under Professor Manfred. Her thesis work was focused on strong field from the very beginning. She was interested in electron correlations and strong field physics, which I had a similar interest in, and Anne and I got to know each other right about that time, as I used to spend time in Paris, supported by NATO, working with, I think, both of us admire a great deal, Pierre Agostini. After graduation, Anne received a permanent staff position at Saclay, and that's when she started her work on searching for photons from these strong field processes, and in '88 discovered this phenomenon which we now know as biharmonic generation. One thing you should know about Anne is she's an incredible experimentalist, but she's an equally incredible theorist. She's been able to bring both forces to bear on kind of introducing this topic to the rest of the world. In 1995, she joined the faculty at Lund University in Sweden, where she's been ever since. Just a little bit about Anne's recognition. She was the recipient of the UNESCO L'Oreal Award. She won the Carl Schweiss Research Award, the Max Born Prize from the OSA, and just this year she was announced as the 2022 recipient of the Wolf Prize in Physics. She's a member of the Swedish Academy. She's the former chair of the Nobel Physics and Chemistry Committee, and she's also a foreign member of the U.S. National Academy of Sciences. So with that, I turn the floor over to Anne.
Okay, thank you very much, Lou, for this great introduction. Can you hear me well?
Yes, we can hear you, Anne. Thank you.
And you can see my slides?
Yes.
Okay, so first of all, let me say that I'm very glad to be with you today, and I am very happy to hear about the NeXUS plans. Sounds great. So I'm going to introduce this field a little bit to you. This is the outline of this talk. First, I will introduce what is HAG and what is the basic physics around this process. And then I will tell you about looking at ultrafast ionization dynamics, looking at electron dynamics using attosecond pulses. And finally, maybe open a little bit the subject towards what I'm calling ultrafast quantum dynamics, which is a new direction where we really want to characterize the quantum states of the photoelectron that we create. So as Lou mentioned, this field did not start by, with the idea to create attosecond pulse. It really started as, let's look at photons in strong field processes. And the idea was to look at fluorescence. And you see here the two first results by the group of Charlie Rhodes and by our group in Saclay, showing these high harmonics. And of course, after these results, the question was raised, are these harmonics phase locked so that they could lead to the production of very short pulses? And this question was answered a few years later with the understanding of the process and especially the understanding of the single atom response leading to the emission of these high harmonics. And here are a few acronyms showing the important steps in this understanding of the single atom response. The numerical solution of time-dependent Schrödinger equation, which was done by Ken Schaefer, Ken Kullander in '92, and then the three-step model, which was proposed by them and by Paul Korkum, and then the strong field approximation, which was proposed by Maciek Levenstein and Mishail Ivanov. All of that more or less the same year. And the strong field approximation was really a quantum mechanical formulation of this three-step model, which you see illustrated here, and where you have first tunneling, and then the electron is propagating in the continuum, comes back, and there is a recombination process leading to the emission of XUV light. And you can look at the different trajectories that are possible. And if you look at the return time of the electron on this different trajectory, you find that it spreads over a few tenths or 100 attosecond. If you look at the spread in return energy of this electron as it come back, you see that the bandwidth is around 10 to a few tenths of eV. And here you have an attosecond electron wave packet, and this property are then transferred to the attosecond pulse. So what is the connection between this and the high order harmonics? Simply, this process is repeated several times with a periodicity which is half the laser cycle. So you have in the time domain a train of attosecond pulses with a sign flip between consecutive attosecond pulses. And if now you go to the frequency domain, then you get your spectrum of high order harmonics with odd orders. So in this description, harmonics are interference of attosecond pulses. You can create train of attosecond pulses, as it's shown here. You can also create single attosecond pulses if you use very short laser pulse to start with. I just want to mention that you can also play with a very short train of pulses, like 2 pulses, maybe 3 pulses, and you can this is an area which I think is being what is fantastic with this field is that this is quite old, 35-year-old, but you still discover new things, you still discover new physics. And for example, I think there is very exciting physics playing with only 2 pulses, maybe 3 pulses, and the control that you have in this case. Now, we are not talking only about single atom response. High order harmonic generation is a non-linear optics phenomenon. It's an emission from an ensemble of atoms. And for this to happen, you need a certain phase matching condition to be achieved. You need to the generating. You need to make the phase mismatch between the generated field and the polarization created in the medium to be equal to 0, as in traditional nonlinear optics. And what is playing a role in this process, you have 4 contributions as written here: neutral atom dispersion, dispersion due to the presence of free electrons in the medium, focusing, and also the effect of electron trajectories, the phase accumulated by the electron trajectories. And you have different signs for this 4 contribution. This is also something that we have studied during 30 years, and you still discover new things. And let me present you a relatively recent result where we think we we got a better understanding of phase matching in these processes, and also an explanation why these sources are so flexible. This plot here shows you the conversion efficiency of the 23rd harmonic in argon. It's just an example. And you have maybe strange unit with pressure times the Rayleigh length. And here you have the medium length in unit of the Rayleigh length. And this is just to account for a geometrical scaling of high order harmonic generation. So just put ZR equal to 1. And so this plot is really a pressure length plot, and the color indicate the conversion efficiency, which is up to just below 10 to minus 5 in this case. So what this plot showed that you can achieve phase matching for high order harmonics generation over a quite broad range of pressure and length. It is located on a hyperbole, and really you can identify two different phase matching regime. The first one is this vertical branch, and here we have a phase matching. The phase matching is very transient. It's governed by the free electron contribution, which compensates the effect due to the neutral atom. This is more or less pressure independent. This is typically the regime that you have when you have a high pressure gas jet. The other regime is this horizontal branch, where which happens at a little bit lower intensity. And this is the case where the dispersion due to the neutral atom is compensated by the effect of focusing. So in this case, we have phase matching, which does not depend too much on the pressure length, and it's very highly dependent on the pressure and gives actually nicer harmonics with more collimated radiation. And this hyperbolic behavior tells us that yes, you can choose a certain medium. You just have to be on this hyperbole to get approximately the same conversion efficiency. And you can explain this huge variety of sources that you can see in the community, from this high pressure gas jet to this long cell or even semi-infinite cell or capillaries. And now let me take you to Lund and show you what kind of source you can build. You can build a intense beamline, and I also show you the name of my colleagues who are driving these beamlines. Here using the Lund terawatt laser, 100 millijoule, 10 Hertz repetition rate. So this is a long beam line with a long focusing geometry. Footprint is about 16 meters. And then on the opposite side, you have a very, very compact light source, where we have here 10 microjoule energy, 200 kilohertz. And this is the laser, and here you have the harmonic generation chamber. So really extremely versatile sources with many orders of magnitude difference in the performances. And there is a huge effort towards milliwatt average power in the sources, or tens of microjoule pulse energy in different groups. And when I saw on internet the performance of NeXUS, my reaction was, wow, you are talking about 10 millijoules, so this is just below these performances here, and 100 kilohertz, which is this repetition rate. So I think this is going to be a great laser to drive these sources. There is behind this beyond this geometrical scaling of this source, there is also a wavelength scaling, which was pioneered by Ludi Moreau, and also driven very much by the group of Margaret Murnane and Henry Captain. You can increase the range in photon energy going into the soft X-ray and range. And you can also play with, and I hope you will do that at NeXUS. you can produce harmonics and attosecond pulse with different polarization states and even with orbital angular momentum. So after this introduction, I would like to move to what we do with attosecond pulse and ultrafast ionization dynamics. And this started actually at the beginning of the millennium with the experimental demonstration that indeed we had very short light pulses when generating high harmonics. So this was done by Pier Agostini, showing that you could have 250 attosecond pulse in a trains, and Ferencross at that time in Vienna showed that you could also produce isolated attosecond pulse. Today the record is 43 attosecond for isolated pulse. In both cases, the method that is used to measure, to characterize this pulse is a cross-correlation method, where you ionize a gas and look at the photoelectrons and measure the photoelectrons as a function of energy, using a combination of attosecond pulses or in a train or isolated, and a probe field, which is the field which is used to create this attosecond pulse at a variable delay. So very rapidly, it became clear that this type of measurement, in this type of measurement, what you get is not simply a replica of the attosecond pulse. Of course, your wave packet is strongly influenced by your pulses, but there is also information about the photoionization process. And what can be measured in this type of experiment is what is called the Wigner time delay. So let me introduce that to you. This is actually a concept from Eugen Wigner in 1955. And the idea is from collision theory, is that when you have an electron, if this electron is colliding with an atom, there will be a certain delay compared with a free electron, and this delay is called the Wigner time delay, and this delay is nothing else but the derivative of the scattering phase. So now in our case, we don't have a collision process, we have a photoionization process. This is half of the process that you can see here. How can you measure these delays? We use an interferometric method or rabbit method. Rabbit for reconstruction of attosecond beating by interference of two-photon transition. This is the technique that was initially proposed by Pier Agostini and his group. And in this technique, you ionize a gas, here neon atoms. So in this case, what I'm going to show you is we are not comparing emission of a photoelectron from an atom and a free electron. We are comparing photoionization from two different subshells of the neon atom, 2s and 2p. So in this rabbit technique, you ionize by harmonics, this blue line, and you look at the sidebands that are produced due to absorption or emission of an infrared photon. So the information here is contained in these sidebands 42 in this case and 44. And we look at the sideband intensity as a function of delay, and we measure the photoelectron spectrum as you see here. And the information is contained in this oscillation here. So what we do here is really measure a time difference between ionization from the 2s shell and from the 2p shell. It's a time different measurement. Our clock is has an hour in our clock is equal to the periodicity of this process, which is half the laser cycle. In this case, it's titanium sapphire, so it's 1,300 attoseconds. So this is 1 hour in our clock. And in this measurement, what we do is we compare the phase of this oscillation for the same sideband here with the one here from the 2s shell We compare to the 2p shell and we measure the time difference. So this difference of time between emission from the 2s and the 2p state. And this is the results. This shown this difference for different sidebands for different photon energy, and this is obtained with different spectra here. And we see that in what we see here is actually an advance of the 2s electron compared to the 2p electron. And there is an extremely good agreement with the theory. So what does it mean? Well, if you look a little bit more at the physics of what we are doing, this delay that we measure is not exactly the Wigner delay. There is, of course, a contribution, which is this Wigner delay, which is physically the time, the propagation time of the electron wave packet in the potential. But there is also an influence of the probe field, which you need to make this interference, to make this interferometric measurement. And this delay, as you can see here, can be calculated very well. You see that it's an advance, it's negative, and actually it looks very much like the experimental curve I showed you before. So let's account for that, and I showed you a difference between 2s and 2p. We can calculate this quantity quite well for neon atoms, and if you look at what is the Wigner delay for 2s electron, what do you find? 0. So in other words, we have done a very complicated experiment to show you that this actually time is very close to 0 within the experimental uncertainty. So this Wigner delay for 2s electron in neon is almost instantaneous within, of course, our experimental precision. Okay, but this is a situation where this is like that. But now, if you look at a more complicated process, if you look at resonance, broadband resonance, like for example the giant dipole resonance in xenon, this is the 4D ionization of xenon. Then you measure time delays in this case, which are absolutely non-zero. Which are a few tenths of attosecond. This is the region of this giant dipole resonance, and you even have 200 attosecond here in the region of threshold, which is influenced by a spin flip dynamics. You can also look at Cooper minima. This is a Cooper minima region in argon, and you see in this case really a non-zero time delays. And you can even see that we don't understand everything. There is a comparison with theory here, showing you a big discrepancy in this region. And finally, you can apply this technique to small molecules and also to much more complicated systems like surfaces, condensed matter. Just to show you a recent result. We have also one question I had in my head almost 15 years ago was, okay, this works very well, but it works in the case of one ionization channel, one angular channel. What happens if we have two ionization channel like S or D? Can we really retrieve the delays for these two different channels in this type of measurement? It's pretty complicated. You have and this is the case of again photoionization of neon, but much closer to the threshold in the 2p shell. Then you have a similar contribution of the S and D channel. So you see that it's if you use this rabbit technique, you will go to P or F final state. And this is only for the m equals 0 state. If you look at the m equal plus or minus 1 state, this channel is not allowed. And so you only have this part, and you need to sum incoherently the contribution of the m and m equals 0 and m equal plus or minus states. So in this case, can we really use technique to measure phases to measure delay? And the answer is yes. You need first of all, you need to perform experiments with angular resolution to have the extra information. This is very similar to actually experiments with synchrotron radiation, where angular resolution gives you information on the different angular channels. And the second condition is to use this universality of the continuum transitions, phases, and amplitude ratio. And doing that, I'm not going to give you more detail here. We can indeed retrieve the delay, this Wigner delay for the different channel S and D, as is shown here. So this is showing the delay in the region very close to threshold. And the physics of this variation that you see here is simply due to the effect of the Coulomb phase for the two channels. So with that, I would like to say a few words about maybe a new area in this field, which is ultra-fast quantum dynamics. And the way we came into this was a kind of continuation of this photoionization time delay measurements. You can use the same technique to measure broadband effects, like I have discussed, group delay, and what is the time scale associated to some broadband resonances. But you can also choose to focus on a much more narrower spectral region where you have a discrete state. And in that case, this measurement is really a phase meter showing the influence of the discrete state, for example, on the phase of the wave packet that you create. And in that case, you use the same technique really to measure a phase variation relative to a certain reference phase. And this is particularly interesting when you have, for example, a discrete state embedded in a continuum, like a Fano resonance. And the prototype of this Fano resonance is the 2s2p state in helium, where you have a rather simple autoionization resonance. And again, the technique consists in looking at the sideband and measuring the photoelectron and measuring both the amplitude and the phase. And you have the result on the right, the amplitude showing a beautiful interference effect due to this. It's an interference between direct photoionization and photoionization via excitation of this discrete state. And the phase variation is show very close to 2 pi jump. And this work is collaboration with the group of Pascal Salière and Luca Agenti and Fernando Martinez theorists. So with that, we are very happy. This technique should work exactly the same way if we look at sideband 40. So let's do that. And well, it works almost the same, but not quite. As you can see on the right, the interference is not as sharp. It does not go to 0. And the phase jump is not as big. It's less than 2 pi. So there is a reduced contrast and reduced phase jump. In other words, loss of coherence. Let me point out is these measurements were done with really a very good spectral resolution. We use even narrowband probe field in order to improve the spectral resolution. So how can we understand this loss of coherence? Well, there is a difference with the sideband 38. There is a 2p2 state, which is very close to absorption of 1 photon here. So it's close to the sideband. And this 2p2 square is interacting with only 1 channel, as I'm going to explain to you in the next slide. So this is now the interpretation of what we see and this apparent loss of coherence. So we have a 2p2 square here, which is interacting with the S continuum. We can go with absorption of 1 photon to a S continuum or a D continuum. So you can write your wave packet as a sum of an S wave and a D wave, and you can separate the radial and angular coordinates. If the two radial part are similar, show the similar energy dependence, then you can factorize this term, and then the 2 degrees of freedom, radial and angular, are separable. If they are not, which is the case of this sideband 40, because of this influence of the 2p2 state, then there is entanglement. And since we are not measuring the angular degree of freedom in this experiment, we average over the angle, then the entanglement results in loss of coherence of the measurements. So pursuing on this idea, we came to the conclusion, okay, that means that we are producing not coherent wave packets, but mixed wave packet. Can we, generally speaking, find a way to measure the quantum state of the photoelectron wave packet and really characterize the density matrix, get information whether we create a mixed state in our measurement or a coherent, fully pure state? And this is an idea which is a new protocol, a new method to retrieve not only the phase and amplitude, but really the density matrix of the photoelectron that we produce. And this method has been called Kraken, which is a Swedish name, and this is an algorithm if you are interested. But anyway, this it's a variation of the rabbit method, where we use not a simple probe field, but a bichromatic probe field with 2 different frequencies, and we can actually vary the frequency difference between these 2 frequency components. Similar to rabbit, we have a delay between the probe field and the XUV field, and we record the photoelectron spectra as a function of this delay and as a function of the energy difference. And by analyzing the photoelectron spectra, we can retrieve the density matrix. And let me show you some prediction. This is in the case of argon. Again, a phonoresonance. In this case, we have 2 final continua because of the spin-orbit interaction. So actually, when we ionize argon close to this state, we create an entangled state between the ion and the photoelectrons, because if we because the ion can be left into the 1/2 state or the 3/2 states. And since we do not measure the ion spin, when we do a measurement, we will induce decoherence. So this is a calculation of the density matrix in this case. So this is an energy plot. And what you see here, you see crosses corresponding to due to the phonoresonance, and you see 2 crosses because we have 2 final continua. And this is a retrieval using the protocol, which shows that indeed this protocol should work to retrieve the density matrix. If the density matrix was round, then we would have a pure states. It's not round, it's elliptic, and this is because there is a loss of coherence. And we can even vary the entanglement in this type of process. If we use a narrow bandwidth, then we have a lot of information whether the ion is in state 1/2 and 3/2 simply by looking at the energy of the photoelectrons, and that means that we have strong entanglement. That means that we will have decoherence and we will have a very elliptic density matrix. And if in contrary the photon the XUV has a large bandwidth, then we will create a much purer photoelectron. The experimental implementation of this is ongoing at this very moment. So with that, I would like to conclude and say that Attosecond sources via HEG are very versatile tabletop sources in the XUV soft X-ray range with ultra short bulk duration. There are many applications. I mentioned what we are trying to do in Lund, with especially in atomic physics. I think it's a great idea to focus a user facility on this. You have the example of ELI, which I think is really coming very nicely at the moment. I think ELI Alps in particular, which is dedicated to Attosecond, is really producing very nice sources. I am very impressed by what you suggest for NeXUS. I think it's a great idea to go towards high average powers for the source, because I think it's obviously there are a lot of application with high average with sources with high repetition rate. So with that, I would like to thank you for your attention and thank my research group that you see here with postdocs and PhD students and senior colleagues. Thank you very much for your attention, and good luck with the NeXUS project, which seems to me extremely exciting. And going back to a comparison with ELI, as far as I can see, NeXUS is going into a slightly different direction. I think using ytterbium as a base, and I think the parameters that you present are very exciting. So good luck with NeXUS.
Thank you. Thank you, Anne. So, okay. So are there any questions? I think we have a few minutes.
Yeah, anyone here in the room is welcome to just raise their hand and ask a question. You are on mic, and anyone who's online is welcome to submit a question through the Q&A.
I'm trying to talk to Sample Chen. Yeah, I'm very impressed by the quantum experiment that your group is conducting. I was wondering, in your opinion, what would be the first killer experiment for this NeXUS state, which has much higher average power and also pulse energy?
I think you are asking a question to NeXUS, right? Or to the NeXUS people?
Yeah,
Or
yeah, I was wondering, would it be more advantageous to use NeXUS to conduct the quantum kind of experiment that you are doing, or do you think there are some other killer experiments that we should do first?
I mean, I can answer one thing, is that the experiment that we plan with this is going to be done with our 3 kilohertz beamline, and we need to vary both the delay as in a rabbit measurement or streaking measurement, but we also need to vary the difference in energy between these two beams. So this is going to be extremely demanding in beam time. So of course, if we could, this experiment would benefit enormously to have 100 kilohertz instead of 3 kilohertz that we have. And there are many similar experiments that would benefit a lot.
Thank you. Thanks for your input.
And I think it's a general, the conclusion is that, of course, we're doing more and more difficult things, and suddenly we would like to have two colors here, and of course we need to so as we want to do more and more difficult things, we need to have a higher repetition rate. So I think this is the right way to go, really.
Thank you. Thank you, Anne.
Are there other questions? from the room or?
So we had a question come in from Matthias Kling. Matthias asks, thank you for the great talk, Anne. I am wondering if and where you see potential applications of measuring Wigner time delays in molecules. Is there something that we can learn from such measurements about complex systems?
I think Matthias Kling is one really doing these measurements in molecules. So I think you know the answer much more than I do. I can answer several ways. First of all, I think there is a way towards the problem of. Now I'm not answering to the right question. I'm answering to the general question: how can we extend this to molecules? One problem is spectral congestion, but I think we are on the way to increase the spectral resolution in our measurements, keeping the temporal resolution. It is a bit contradictory, but it's not. And we are doing this by several tricks, by repetition, by using several pulses in order to have high spectral resolution. So I think there are ways around to this spectral congestion problem that you have in molecules, using, for example, 2 XUV pulses as one idea. So that's one thing. What can you learn? I'm not a molecular physicist, but I can answer more generally the following way. I mean, just looking at atoms, you learn a lot, because you learn, I mean, this is giving you otherwise you can only get cross section. So you get the amplitude and the phase. And of course, a lot of information is contained in this phase. So I think the same should apply to molecules. This is my way to answer to you. I don't know if you are happy with that.
Yeah, other questions? And I just like add to what you just said. I mean, another way within the, using the Attosecond techniques would be to use this idea of like, quantum trajectory selection to kind of disentangle all this spectral conjecture. Very similar to like when you did the quantum stroboscope, right?
Yes. So what is your question?
Oh, there's no question. I'm just a
yes.
comment.
Yes. Yeah, I agree. I agree with you. But I think there is really a lot to do. I mean, in using these techniques in chemistry, multidimensional spectroscopy, one has to apply this technique to, into the XUV. But I am convinced that one should not give up with molecule. Oh, this is too complicated. But one should work on this spectral resolution and also, using chemistry techniques.
Okay. Any additional questions online, TJ? Last chance for the room.
Let me ask the final question. When you did your neon 2s2p delay, you showed some error bar in delay data. What is the major origin of the error bar? Which seems to be, for instance, neon 2s, we thought delay is almost 0, but the error bar is bigger than the delay itself. What is the major source of the error bar?
I think in our case, it was the temporal stability of the interferometer. I think since this experiment, we have actually improved it by a factor 2 or 3. So now we are at the level of 10 attosecond. So in this experiment, it was this temporal stability of the delay, due to the spectral interferometer.
Okay. Well,
I don't think. I think we have not. I think we can do better. And this is also a reason why I think I mean, it's easy to think, oh, HEG or Attosecond, you don't need a user facility because you can have that in your lab. This is a tabletop source, yes. But if you want to have to really push towards high precision, towards repetition rates, high average power, I think a user facility is going to be very important. So, and I see that with Eli, which is coming to age. I mean, it's really starting now. We haven't had any facility before, so it's really new, and it will be very interesting to see how it works and what are the new results coming due to these user facilities.
Thank you.
Okay, I think we have to move on, and thank you again for taking the time out of your schedule to be with us today.
Thank you. So I will stay online anyway, so.